A very good morning to all of you. So we have here for special lecture on Signal and System BEC 403, and that is intended to the students of BTech. And today we are going to discuss about Introduction to Signal and System. So how the signals are represented in the form of mathematical equation as a function of independent variable, and then we transform that or apply that signal into a system, and to see what is the response of that system, we will look into this lecture. So here we are going to see what are the fundamentals of signals and systems. So signals are basically, as I have told you, a function of one or more variables that convey information on the nature of a physical phenomena. So example we have here, that is like a voltage source, a current source, or a simple signal which can be represented as x of t, heartbeat, a blood pressure or temperature vibrations, etc. Or you can have here, you can see that small t is the independent variable. So signals can be represented as a function of one or more independent variable. According to that, it is characterized into one-dimensional signal and multi-dimensional signals. So you can see from here that for one-dimensional signal, the independent variable is only single. For example, a speech signal. The speech signal is basically acoustic pressure as a function of time. We can represent a speech signal. Similarly, we have multi-dimensional signal where there are more than one independent variable, then that signals are called multi-variable signals or multi-dimensional signals. So basically we look into the time, which is there the independent variable. So whatever the mathematical expression we write in this course is as a function of time. So we represent here signal as x of t. And this representation is for continuous time. So there are two type of signals, basically continuous time and discrete time signals. So for the representation of continuous time, we represent here as a function of a small t. Similarly, for discrete time signals, we represent as a function of a small n and in a square bracket. So we represent here a signal as x of n. So you can see for discrete time signals, it is represented as x of n, and for continuous time signal, it is represented as x of t. So if we see the system, which is very important part of this course, obviously, because without system, we cannot see the response of the particular signal which is applied on the system. So a system is an entity or operator that manipulates one or more signals to accomplish a function, thereby yielding a new signal. Or you can say that for getting the response of the signal, we have to apply a input signal, which is of course a continuous time signal, or it can be a discrete time signal like this, and we obtain a output signal which is also of continuous time signal or discrete time output like this. And system has some response which is called as impulse response, and it is represented as ht. So here h of t is impulse response of the system. So we see here, we will look into this course that how you can obtain your output yt with the help of this input signal xt and the impulse response of the system ht. So commonly encountered systems, basically communication systems like automatic speaker recognition system, aircraft landing system. So these are some examples of the systems in which we apply some sort of signal and we obtain some responses from that system. So if we classify the signals into categories, then there is first type of signal, which is continuous and discrete time signals. So continuous signals are those signals which take the continuum of all the values of the time period, and it shows all the amplitudes for every values of the time. Either it can be a integer value or it can be a fractional value. On the other hand, discrete time signals only can be obtained for the integer values of the n. So the axis also changed. Here you can see from the first figure it is xt versus t, and in the second figure it is xn versus n. So here we took n is equivalent to 1, 2, 3 and so on. But for time t, we can use any value of the time period, and for that value we have some amplitude. But for discrete time signal, we have only for integer set of values of n. Only in that case we obtain some amplitudes. So this is the major type of classification of signal, which is obviously a broad category, continuous and discrete time signals. So for many cases, xn is obtained by sampling xt. You can also obtain your xn, which is the discrete version of the analog signal or the continuous time signal, by sampling with by sampling theorem, or by sampling it with a value, that is xn is equivalent to xn t for n equivalent to 0, plus minus 1, plus minus 2, and so on. So are there any requirement for the sampling? So yes, there is requirement for the sampling if we want to convert a analog signal directly into a discrete form of signal. Then with the help of the Nyquist criteria, which is a very important sampling condition, we will see this also in our course, which is fs should be greater than equivalent to twice of fm. With this sampling frequency, we can sample that signal, analog signal, into discrete form of signal. So next category is even and odd signals. So even signals are those signals in which we have a reflection, that is x of minus t, and we obtain the same signal in the same sort of signal like this. So if suppose this is a signal minus 1, 0, 1, and the amplitude is 1, and this is xt. So obviously x of minus t is the time reversal, and for time reversal we flip the signal around the y-axis, and you just obtain the same signal, which is x of minus t. So here we can see that x of t is equivalent to x of minus t, and that's why it is called as even signal. So if we take a mirror image around the y-axis and it comes out to be the same signal, then it will be even signal. On the other hand, if we take the mirror image around the y-axis and then taking the mirror image around the x-axis and the signal becomes same, then it is called as an odd signal. So for odd signal, it is x of minus t is equivalent to minus of xt, or in discrete form, it is x of minus n is equivalent to x of minus of x of n. So the negative sign outside shows the reflection around the x-axis. The negative sign inside the bracket is the reflection around the y-axis. Any signal xt can be expressed as a combination of this both signals, that is even and odd signal. So xt can be represented as xet plus x naught t. Similarly, x of minus t can be represented as xet. Obviously, x naught t is minus of x naught t, and thus we can obtain two equations here. First one is for the even component of the signal, and the second one is for the odd component of the signal. So even component can be found by xt plus x of minus t divided by 2, and similarly odd component can be found by xt minus x of minus t divided by 2. So by this way you can solve various questions based on even and odd signals. The third category is periodic and non-periodic signals. So if a signal repeats itself after a certain period of time, then that signals are called periodic signals, and obviously the condition necessary condition is from the signal must be from minus infinity to infinity. So here the equation, important equation is this: xt is equivalent to xt plus t. So here xt is equivalent to xt plus capital T, or we can have xt is equivalent to xt plus mt, where m is an integer value, m is equivalent to 0, 1, 2, 3 and so on, like this. So for this equation we can have some fundamental period, which is the smallest integer value. We cannot put 0 here, fundamental period. So t naught will be the fundamental period, which is equivalent to the smallest integer value of the capital T. For example, like sine or cosine has a waveform which has a periodicity of 2 pi. It can be periodic with 2 pi, 4 pi, 6 pi, 8 pi and so on for the odd even number of periods. But the fundamental period is kept to be 2 pi because it is the smallest integer value. Similarly, for discrete time signal, it is xn is equivalent to xn plus capital N, where capital N is the fundamental period, or n naught you can represent as a fundamental period. With the help of formula f is equivalent to k by n, we can find out the value of capital N here. So the next category is deterministic and random signal, which is also a broad category of signal. So deterministic signals are those signals which can be specified with the help of mathematical expression, and there is no uncertainty in these equations. On the other hand, random signals are those signals which has some uncertainty, and these type of signals can be calculated with the help of probabilistic nature or probability theory. So for random signal, for example, a thermal noise, weather forecasting, which is obviously a random kind of a signal. On the other hand, if we represent xt is equivalent to a sine omega naught t, like this, and where t lies between from minus infinity to infinity, these kind of expression which can be represented as a mathematical form, it is always a deterministic signal. So in this course we are using these deterministic signals to calculate the signals, or to analyze the signals, or to calculate the response of the system, and then we see the frequency domain representation of also these kind of signals. Next category is energy and power signals. So energy signals are those signals which are obviously bounded signals and which are non-periodic in nature. So if you see the periodicity, the periodic signals are those which are from minus infinity to infinity. But in the case of energy signals, these signals are always bounded. For example, a rect signal like this is rect t by 2. And these type of signals, we can have a finite energy, and if you calculate the power here, because power is equivalent to limit t tends to infinity, average power, energy by time. So if we limit, if we have finite energy and t tends to infinity, then the power, average power becomes 0. So if the energy is finite, average power is 0. So there are three classification in energy and power signal. First is if the signal is energy signal. So if energy signal is there, then the energy is finite and power become 0. Similarly, the second form of signal, when power signal is there, power signals are there, so power is finite, average power is finite, but energy is infinite. And the third form of signal, neither it can be an energy signal and nor a power signal. So for calculating the power or energy, we have represented here these formulas. So for calculation of energy, you can use energy is equivalent to minus infinity to infinity mod of xt ka square or x square t dt. Similarly, for power, limit t tends to infinity 1 upon 2t minus t to t. If there is range from minus t to t, then it is 1 upon 2t. Otherwise, if it is 0 to t, then it is 1 upon t, or 0 to 2t, it is 1 upon 2t. So whatever the integration range is here, that is 1 upon 2t here. So this is x integration over x square t. So this part is basically energy. Energy by 2t is your power. So for discrete time signal also, because these are discrete time signal, we use here summation in place of integration. So energy is represented here as energy is equivalent to n equivalent to minus infinity to infinity mod of x n ka square. You can also write like this: energy is equivalent to summation over n equivalent to minus infinity to infinity mod of x n ka square. Similarly, average power here, because there are terms from minus infinity to infinity, if you calculate the terms, suppose from minus 3 to 3 you have to calculate. So there are 7 terms, minus 3, minus 2, minus 1, 0, 1, 2, 3. So there are one extra term as compared to the integration in continuous time. So average power can be represented as limit n tends to infinity 1 upon 2n plus 1. This 1 is basically for the extra term, that is at n equivalent to 0, n equivalent to minus n to n mod of x n ka square. So this is these are the formulas for calculating the energy and power here. So now we have another broad category which is obviously useful in different courses like communication engineering, digital communication and all. So analog signal and digital signal. Obviously analog signals, you know, that is in a nature which is continuum of taking continuum of values of the time period t, and for the discrete case it is the sampled version of the continuous time signal. So another category here is for the discrete values of the signals, where we take only some values which is with the help of the quantization and all, and we see how the discrete time continuous time signal is converted into a digital signal here with the help of these quantization methods. So now we look into the basic operations on signals. So we can have various operations on signals. We can have amplitude scaling, addition, multiplication, differentiation, integration, time scaling, reflection or time reversal, time shifting, combination, etc. So we can see here one by one what is amplitude scaling. We just increase the amplitude of the signal, that is called as amplitude scaling. So if yt is equivalent to c of xt or c of xn, where c is the gain, c can be greater than 1 or c less than 1, according to that the signal will be transformed. Similarly, addition of the two signals is simple. simplest, that is yt is equivalent to x1t plus x2t or x1n plus x2n. Similarly, multiplication x1t multiplied by x2t, differentiation d by dt of xt. Similarly, in the discrete time, it is not differentiation, it is a difference equation, that is xn minus 1. Integration minus infinity to t x of tau d tau. In the discrete case, there is summation. Time scaling, we have two types of time scaling here, compression and expansion. That is x of at, or if a is greater than 1, that is it is compression. If a is less than 1, then it is expansion. Similarly, yn is equivalent to x of kn. In the same way, if k is greater than 0, then there will be compression, and if k is less than 0, then there will be expansion. Reflection, yt is equivalent to x of minus t, which we have already seen in that even and odd signal. Similarly, yn is equivalent to x of minus n. In the time shifting, we have two operations. One is delayed and one is advanced. If yt is equivalent to xt minus t naught, this is delayed signal. If t naught is positive, agar t naught आपका positive है तो in that case, if x, you can have t plus t naught, this is advanced signal. So we have, for delayed signal, the signal will be goes to the right by the amount t naught, and for the advanced signal, the signal will be goes to left for the amount of t naught. Similarly, we have combination of these type of signals, that is, if we represent yt is equivalent to x of a t minus t naught. So in this case, we have all the things, that is scaling, shifting, and obviously we can have amplitude scaling. Suppose a multiplied by x of at minus t naught. In that case, we use the simplest method, that first we do shifting, then we do scaling, and then we do reversal. So you have to keep in mind that following this shifting, then scaling, then reversal is better than if you change the following, like scaling is first and shifting is next and reversal. Because if you scale first or shift first, scale first or reversal first, then there will be possibility that shifting will be vary according to the advanced and delayed method, which you have already earlier used in the previous things. So rules here are very simple. So suppose, for example, yt is equivalent to x2t plus 3. We have a xt signal and we have to find out x2t plus 3. So firstly, we just scale it for xt plus 3. Then that will be a advanced signal. So minus 1 will come to be minus 4 and 1 come to be minus 2. So it is from minus 4 to minus 2. And then we use scaling, because it is x of at and a is greater than 1, then there will be a compression, which is divided by 2. So it will be from minus 2 to minus 1. Amplitude, there will be no change in the amplitude. So there are some other signals like exponential, sinusoidal. So exponential signals are x t is equivalent to e to the power minus at or b e to the power at, where a can be a positive variable or a negative variable. So a can be due to this a, if a is less than 0, then it will be a decaying type of signal. If a is greater than 0, then it will be a growing. If a is equivalent to 0, then that will be a DC signal. Similarly, for sinusoidal signal, a cos omega t plus phi or a cos phi omega n plus phi, in this type we can represent continuous and discrete time signal. So now we have a very important category which is called as unit step function. So ut is defined as 1 for t greater than 0 and 0 for t less than 0. Similarly, un can be defined as 1 for n greater than equivalent to 0 and 0 for n less than 0. We have unit impulse function which is represented by del t. So it has a property that minus infinity to infinity del t dt is equivalent to 1 for t equivalent to 0, and elsewhere it is 0. So we can have this property of the impulse function. Similarly, for discrete time, del n is equivalent to 1 for n equivalent to 0 and is equivalent to 0 for n not equivalent to 0, or elsewhere it is, everywhere it is 0 except at n equivalent to 0, you can say. So unit ramp function, rt is equivalent to t for t greater than equivalent to 0 and 0 for t less than 0. RT can be represented as t of ut, or ut can be represented as differentiation of RT. We can have in the discrete domain, that is R of n. is equivalent to n for n greater than equivalent to 0 and 0 for n less than 0. So now we look into the system properties. So as we have already discussed about the signals, the systems are basically a block in which we are applying some sort of input and we are getting some output. So the first figure showing here is the continuous time system. The second figure is for discrete time system. So in the continuous time system, we have the input as a continuous signal and the output also as a continuous signal. In the same way, in the discrete time, the input as a continuous input and the output as a continuous output. So here H represents the system. So we can have, there are some properties of this system. That is, first one is the stability. We have to see whether it is bounded input and bounded output. It is called BIBO stability. So if we check, if we are giving the input as a bounded signal, we think that the output must be a bounded output. So if it is happening, then it is a stable system. Otherwise, it is unstable system. Next category is memory and memoryless, or we can also write it like static and dynamic. So if it is a static system, then it is without memory, and if it is dynamic system, then it is with memory. So another name of memory and memoryless is with memory is dynamic and without memory is static. So if the output depends on the only on the present values of the input and not on the past and the future values of the input, then it is called static system. Otherwise, it is a dynamic system if the output depends on the past or the future values of the input. So for example, here yt is equivalent to 5xt plus integration over minus infinity to t x tau d tau. Obviously, this showing the only the present value. If we put t equivalent to 0, 5x of 0, t equivalent to 1, 5x of 1, like this. But here minus infinity to t, because it is from minus infinity to t, it consists of some past values also, not only the present value. Then this type of systems are basically dynamic systems or memory systems. So you can write also dynamic systems. On the other hand, for example, memoryless system like yn is equivalent to xn plus x square, and we put y of 1, it is same as x of 1 plus x square of 1. So it is for every instant of time, if we are taking t equivalent to 1, it is depending on the input values at t equivalent to 1, not on the previous value and not on the future values. Then these type of systems are called memoryless systems or static systems. So next we have causal and non-causal systems. It is similar to static and dynamic system. For causal system, the output depends on the present and the past values of the input. But for non-causal, it depends only on the future values of the input. With the present value, it can also depend on the future values of the input. So we can say that all the memoryless systems are causal systems, but all the causal systems are not necessarily to be memoryless system. The other category of the system property is time invariance, or it can also be called as time invariant system. So if we are delaying the input as xt minus t naught, and according to that, the output is also going to be delayed by yt minus t naught, then that systems are called time invariant system. For example, yt is equivalent to x of t minus 3, for example, like this. So if we delay the input, that is x t minus 3 minus t naught, like this, and if we delay the output, this is called as input delay, and if we delay the output yt minus t naught, then it is x of t minus t naught minus 3. Both are different equation, but the values are same, because xt minus 3 minus t naught is the input side delay and yt minus t naught is the output side delay, which is similar as x of t minus t naught minus 3. So if both are same, then it is called as time invariant. On the other hand, if we write like this, yt is equivalent to x of 2t. So in this case, the input delay is x of 2t minus t naught, but the output delay is, that is yt minus t naught, which is equivalent to x of 2t minus t naught minus, 2 minus t naught, which is x of 2t minus 2t naught, which is different. So this value, whatever I have calculated in the input side, are not equivalent to the output side. So in this case, the system is time variant system. Next is linearity. In the linearity, we supposed to follow the two principles, that is, one is superposition and the another one is homogeneity. So in the superposition, we add the two signals and apply to the system, and we get the output as the addition of the two outputs, like x1t plus x2t will give you y1t plus y2t. If it is following the homogeneity also, then a x1t plus b x2t is equivalent to a y1t plus b y2t, where here a and b are the arbitrary constant. So there are two properties, superposition and homogeneity. So we apply these properties on the system, and then we check whether the output is same as a y1t plus a y2t. If it is existing like this, then it is a linear system, otherwise else it is a non-linear system. Next is time variant invariant, which we have already discussed. That is, time variant is xt minus t naught is giving you yt minus t naught, otherwise it is time variant system. All about this for the today's lecture, and then we will discuss in the next lecture about the system properties, some properties of the system like LTI and LSI system. In that we have convolution, convolutional integral and so on, and then we discuss about the frequency representation of these kind of signals, like of Laplace transform or Z transform or Fourier transform itself. So thank you for today, and we will meet in the next lecture.